Forces in a magnetic field. A magnetic field. A magnetic field is detected by a compass. Supposing there is a bar magnet. A bar magnet has two poles. These are the North Pole and the South Pole. When a compass is brought near to a bar magnet, the pointer of a compass will change its direction. As the compass is moved around a permanent bar magnet, the pointer of the compass somehow follows a certain line, and this line is called a magnetic field line. A magnetic field describes the magnetic influence on an electric charge, an electric current, and magnetic materials. Magnetic field visualization. Supposing this is a single strand of a magnetic field line. And the direction of the path of a magnetic field line is given by the direction of the arrow. Where the magnetic field line is directed, it will be symbolized by a circle with a dot at the center. And where the magnetic field line is moving away from, is represented by a circle with a cross at the middle. So this illustration represents 9 magnetic field lines that are moving towards the observer, while the other illustration, or the other 9 magnetic field lines, are moving away from the observer. So again, this is an illustration of a bar magnet along with its magnetic field lines. Notice the direction of the magnetic field lines. The magnetic field line originates from the North Pole and is directed towards the South Pole. The magnetic field lines also describe the direction of a magnetic force. Although one cannot see a magnetic field line, it is a visual representation of a magnetic field. But one, however, can trace a magnetic field line, and that is by the help of an iron filing. If an iron filing is sprinkled over a bond paper, for example, where a bar magnet is placed below, the magnetic field line of the magnet can be traced by the arrangement of the iron filings. The magnetic force. Supposing there are several magnetic field lines that are directed towards the observer, and if a particular charge given by the symbol Q is found to be within these magnetic field lines, as the charge moves, its movement is perpendicular to these magnetic field lines since its velocity is towards the left or along the x-axis. And since the magnetic field line is towards the observer, then this will be the z-axis. While the force of this charge will be perpendicular to the charge velocity, at the same time perpendicular to the magnetic field line. So this will be the representation of the three-dimensional perspective view between the magnetic field line, the direction of the velocity of the charge, and the force within the three-dimensional space. So the x-axis is the direction of the velocity of the charge, and the y-axis is the force of the charge. And the z-axis is the path of a magnetic field line. The three components, namely the force of the magnetic field, the velocity of a charge, and the path of a magnetic field line, can also be visualized by the right-hand rule, where the thumb of your right hand will represent the force of the magnetic field. The point finger will represent the direction of the velocity of the charge, while the middle finger will point to the direction of the path of the magnetic field line. The magnitude of the force, which is given by the symbol capital letter F. This is the force experienced by the moving charge in a magnetic field. The magnitude of this force is dependent on the product of the four factors. These are the Q, or the charge, that is expressed in coulomb, the V, expressed in meters per second, is the velocity of the moving charge. The capital letter B is the strength of the magnetic field, and the sine theta is the angle between the field or the magnetic field lines and the direction of the velocity of the charge. This is expressed by the equation capital letter F, or F sub m, is the magnitude of the force, Q is the charge, V is the velocity of the charge, capital letter B is the magnetic field strength multiplied by sine theta. In this example, a uniform magnetic field B is equal to 3.0 Gauss. Gauss is equal to 1 times 10 raised to the negative 4 Tesla. Exists in the x direction. A proton, Q is equal to positive E, or the value for the elementary particle, shoots through the field in the positive y direction with a speed of 5 times 10 raised to the power of 6 meters per second. The requirements are to find the magnitude and direction of the force on the proton. Here we have the coordinates of x, y, and z. Notice that B, or the magnetic field, lies along the x direction, while the direction of the velocity of the charge Q, or the proton, lies along the positive y direction. Since the force is perpendicular to the magnetic field and the velocity, this simply means that the force is directed towards the z direction. This leaves us to just calculate the magnitude of the force on the proton. Since the magnetic field is equal to 3.0 Gauss, this is also equivalent to 3.0 times 10 to the minus 4 Tesla. Using the formula, F sub m is equal to Q V times B sine theta. Q is the value of the elementary particle, which is 1.6 times 10 to the minus 19 coulomb, multiplied to the velocity, which is 5.0 times 10 to the positive 6 meters per second, multiplied to the magnetic field, which is 3.0 times 10 to the minus 4 Tesla times the angle between the direction of the velocity of the charge and the magnetic field line, which is equal to 90. Therefore, sine 90 degrees. So to answer letter A, the magnitude of the force on the proton is equal to 2.4 times 10 to the minus 16 Newton, and the direction of the force is directed towards the z-axis. Therefore, to illustrate the magnitude of the direction of the force, since the force is perpendicular to the path of the magnetic field lines and perpendicular to the direction of the velocity of the charge, the force, therefore, is along the z direction. The force on a current in a magnetic field is given by the equation delta F sub m is equal to I times delta L times B times sine theta, where delta F sub m is the change of the magnitude of the force in newtons, and I is the current. Delta L is the small change of the length of the wire, and B is the magnetic field or the magnetic field strength in Tesla multiplied by sine theta. However, for a straight wire of length in a uniform magnetic field, instead of using delta L, it only uses the capital L, which is the length of a straight wire. The magnetic field is out of the page. In other words, the magnetic field line path is moving towards the observer. B is equal to 0.80 Tesla, and the wire shown carries a current of 30 amperes. The requirements for this problem is to find the magnitude and direction of the force on a 5.0 centimeter length of wire. This problem is dealing with a 5 centimeter length of wire. Therefore, the formula to be used is delta F sub m is equal to I times delta L for a short piece of wire multiplied to B times sine theta. I is equal to 30 amperes, while delta L is equal to 5 centimeters or equal to 0.050 meter times 0.80 Tesla, and sine 90 is equal to 1, so delta F sub m is equal to 1.2 Newton. By the right-hand rule, the force is perpendicular to both the wire and the field and is directed toward the bottom of the page. Supposing we have two magnetic poles, the north and the south. The two magnetic poles will generate a magnetic field. The magnetic field B is equal to 0.25 Tesla, while a loop of wire is situated at the center of the magnetic field, experiencing a current of 2 amperes. So what will be the force on each vertical wire? Since force can be calculated only to the vertical wires, because this is the wire that is perpendicular to the magnetic field line. And so we are going to make use of the formula F sub m is equal to the current times the L and not the delta L, since this is a 12 centimeter wire and we consider this as a long length of wire multiplied by B times sine theta, which is 90, which is equal to 1. So I is equal to 2 amperes times L, which is equal to 0.12 of a meter, times the magnetic field, which is equal to 0.25 Tesla. And so the force on each vertical wire is equal to 0.060 Newton. Torque on a flat coil. Remember that torque is first introduced in the topic in mechanics. Torque is actually a product between the moment arm times the perpendicular force, and torque is also applicable on a flat coil, and an application to this are meter scales. And so this is given by the symbol tau, which means torque, and torque or tau is equal to N, which is the number of loop in a coil, times I, which is the current, times A, which is the area of the coil, times B, or the magnetic field strength, times sine theta. Now the 40-loop coil carries a current of 2.0 amperes in a magnetic field B is equal to 0.25 Tesla. What will be the torque and how will it rotate? Again, torque is equal to N, which is the number of loop of the coil, times the current, times the area of the loop, times B, which is the magnetic field, times sine theta, which is sine 90 degrees, where N is equal to 40 loop and I is equal to 2.0 ampere, while the area A is equal to 10 centimeters by 12 centimeters, or 0.10 of a meter by 0.12 of a meter, times B, which is equal to 0.25 Tesla, times sine 90 degrees. Torque is equal to 0.24 Newton meter.